Hi everyone, welcome back to 30.100. This is a lecture that you will need for week 3 of computational and data-driven engineering. So the main topic this week will be factorial designs, and it's mainly chapter 7 of Montgomery's book. There'll be one video, four case problems, and a project that you will have some time in the class to do this week, or in week 3, and also in week 4 we'll allocate some time for working on this project. So the book chapters that you should read, the book section 7.1 to 7.32, this introduces the concept of factorial designs. We'll skip a little bit and then talk about designing with more than 2 factors, which is 7.34 of Montgomery's book. And then finally, we'll look at how we can use a sub-fraction of the designs to actually get a lot of information, and that will save us a lot of time because we won't need to do so many experiments or produce so many prototypes. So this map shows us what we've done so far. In week 1, we started looking at errors and the different types of errors. And then we looked at how errors build up. So if you have a system of many components that have to work together, those components also have an error or a performance distribution, and that will affect the overall performance of the system. And we analyzed how these different components can affect the performance of the system, both using a Monte Carlo approach, a numerical approach, and also an analytical approach. In particular, from the analytical approach, we could identify or break down the overall system error into different contributing factors. And then in the last week, we looked at single factor ANOVA. So for example, if you had a system that relied on 3D printed parts, and maybe the quality of the 3D print affected the performance of the system, we could try to use ANOVA to identify and optimize the factors that are significantly affecting the quality of the 3D print. That would be a single factor experiment. Maybe the factor would be temperature of the extrusion of the filament, the 3D printed filament. And then we might perform that experiment at many different temperatures to see which one led to the smoothest print. And then we could do a statistical analysis to see if it really is statistically better than the other prints. So we could think of optimizing the individual components using ANOVA, and then that would improve their performance, and so they would contribute less to the system error, and the overall performance of the system would improve. This week we're going to take this idea one step further, and we're going to go deep on ANOVA, and we're going to use it for designing experiments. So after this week, you should be able to design and conduct experiments involving several factors. So far, we've only really looked at single factor ANOVA, but we might also extend this to multiple factors. For example, keeping with the 3D print analogy, we might have a factor which is temperature, which is the experiments that we were doing before, and we might also have another factor which is the speed that we print at, and both of those factors might contribute together to create a particularly smooth print. We'll be able to analyze with statistics whether these particular factors are affecting the print or if they're not doing anything. So you'll need to learn how to analyze and interpret main effects graphs and their interaction graphs. We'll also need to learn how to do multifactor ANOVA to analyze the data from these multifactor experiments, and know how to use 2-level factorial designs, and finally be able to reduce the number of experiments that we have to do by using something called fractional factorial designs. So let's imagine that we've just bought a new 3D printer and we don't really understand the optimal settings for printing an object, and we just try the standard settings and we get something that looks horrible. So here is a 3D printed boat, and you can see that the layers, you can see the individual layers, and the quality of the print is very bad. The shape looks slightly deformed. So we're slightly worried and somewhat angry with how this printer is performing. So then we think, okay, maybe the reason for this print performing so badly is the temperature, or the temperature of the PLA that we're printing, or it might also be due to the speed that we're printing at. So we might conduct some experiments to try and optimize these settings. For example, we might try printing at different temperatures, or we might try printing at different speeds, or we might try both. So let's imagine this scenario. So first of all, in our first experiment, we might try printing at 180 millimeters a second, which is slightly faster than what we were printing before. But because we're good experimentalists, we think that it's a good idea not to change too many things at once. So we will keep the temperature fixed at 190. And then we find a roughness of 0.63 millimeters, a very rough print. And then for our second experiment, we have a breakthrough. We reduce the speed of the print, and the temperature we keep at 190, and we see that we halve the roughness. So we conclude that, well, we don't conclude at this point, but we are hopeful that we found the source of the problem. It's something to do with the print speed. But then we do a third experiment, just to test whether temperature is important or not. And we see that at the higher temperature, the roughness goes up. So then from these three experiments, we can see, okay, roughness really didn't go up too much when we increased the temperature. It went from 0.3 to 0.36. But the major factor seemed to be the velocity of the print, the speed of the print. Going slower seemed to produce a good print. So then we're happy, and we stop at that point and just think, okay, the settings really depend on the speed of the print. But we might have lost a trick. This is called, by the way, this is called a one factor at a time experiment. We change one factor at a time, which is normally good advice, right? But it's actually not so optimal way of quickly searching through the parameter space to see which variable is affecting the output of an experiment. So we change, first of all, we change the speed, and then that factor's done, we've seen it has an effect, and then we change the temperature, and we see that that doesn't really have such a big effect. So after these three experiments, we could pretty much conclude that velocity has the biggest effect using this OFAT, one factor at a time approach. However, there's something called an interaction that often happens between parameters, between factors. In this case, we have the speed factor and the temperature factor. If they interact, you might get a really interesting result. We've already concluded that this might be the best setting, but we didn't actually try a different combination, which is the high temperature and high speed. So if we'd done that, we might have found a new result which could be even more interesting. For example, the speed and the temperature might have interacted to give a much smoother print than any of the results that we would have got from just checking one factor at a time and jumping to conclusions. Effectively, we've jumped to a conclusion in the OFAT experiment and missed this important result. So OFAT is often used, especially by non-experts, but there are better methods, more efficient methods for doing design. So these are the issues with this OFAT, one factor at a time process. It often misses interactions. Many measurements are required to reach a certain level of accuracy, especially if you, in this case, we're just looking at two levels of each factor, but maybe you might go from, say, 130 to 180 millimeters a second, and then decide, oh no, that both of those are too fast, so I should go down to another speed and see how that happens. And then maybe I should try a slightly different temperature, and then it will take you a long time to converge on a solution or converge on an optimum. So if we can generalize this approach and maybe look for trends in how the system behaves and then use those trends to identify the best conditions, that is much better than just doing one factor at a time. So one factor at a time requires many measurements, and it's difficult to test whether these factors and interactions are actually statistically significant, because usually with one factor at a time you might make only one measurement and there's no group or no group of measurements with the same settings to have some sort of variation to see if this is significant or not. So this brings me on to factorial designs. So these are used to improve, say, a process, or to try many different combinations of parameters, or even in a design to try many different configurations to quickly converge on an optimal solution. And we will be using it in the 1D project for designing a propeller. So in the previous example, we imagined the effect of speed and temperature on the quality of, or roughness of a 3D print. And we analyzed the quality at each combination of speed and temperature. So because there are two factors, we had four possible experiments that we would need to do, four different prints that would need to make and then evaluate the quality of the surface finish. We might have also imagined a third factor, which could be the feed rate. That's the rate that you push the filament through the printer nozzle. Then we would have four levels, so 2 levels for each factor, and two factors at one feed rate, and another 2 factors with 2 levels at a second feed rate. So we'd have in total 8 different experiments that we would need to measure the roughness at. So this table here shows the different combinations. I'm using this coding where -1 means for the lower temperature setting, or the lower setting, and +1 means the higher setting. So in this case, this would be the lower temperature. In the example before, I think I used 180 degrees C or 190 degrees C as the lower setting, and 1 would represent the upper setting, which I think is 210 degrees C. And the speed, I think I used an example of 130 millimeters a second for the lower setting, and the higher setting would be 180 millimeters a second. And similarly, we could have 2 settings for feed. Because we're only looking at 2 settings or 2 levels for each factor, we have 2 possible levels, and then there are 3 factors. In this case, 3 factors, so K is 3. That means we would have 8 different experiments, or 8 different combinations of experiments that they would need to do in order to analyze the roughness effect for all of these different, for this combination of 3 factors. So here is the same table again, only this time I've made a new column for the results of the experiments. So there's every possible combination of this 2-level experiment of temperature, speed and feed. So there's 8 different combinations of these 3 factors. And then I have 8 results for each possible combination. Now here's the interesting point. We actually have 4 measurements where the speed is low, or the temperature is low, and we have 4 measurements where the temperature is high. And the same applies for speed. We have 4 with the speed low, and 4 with the speed high. And of course the same applies for feed. So we can actually calculate the average effect of the temperature being low with the other 2 factors changing, and the average effect of the temperature being high and the other 2 factors changing. And we can plot it. So for example, if I wanted to see the effect of temperature, where the average effect of temperature, I would just look at the temperature, the results when the temperature is low, all 4 results when the temperature is low, and calculate the mean value of the roughness when the temperature is low. There's an n here. N represents the number of samples that you take to get each of these results. So I've put R1 here, but R1 might be several measurements at R1. You might, instead of measuring the roughness one time, you might measure it n times. N can be one in this particular example, but usually you'd measure it multiple times. And then you'd get a mean roughness of the sample when the temperature is low. Similarly, when the temperature is high, we can do the same thing. Take the roughnesses when the temperature is high and divide by the number of measurements that we made. So then we can make a line graph. So we're assuming that the roughness responds linearly to temperature in this case. So we can look at the difference between the effect of temperature when the roughness is high and the effect when the temperature is low, and we can make up what's called a main effects graph. So we have the temperature, the coded value of the temperature on the x-axis, and the change in roughness on the y-axis, and we can see that generally as we increase the temperature, in this particular example, the roughness gets larger. So we can see that the trend is that a lower temperature might produce a smoother film over this temperature range. Okay. Then for each group, so for each of the groups where the temperature is low and each of the group where the temperature is high, we've got 4 measurements, so we can actually have a distribution and plot on here something like the standard deviation, if you like. So we can really see so this actually represents how the roughness is changing at a fixed temperature when all of the other factors are changing, which is. So to reinforce this point, I'm going to do now the example where the speed is the main factor that we're interested in. So first of all, I select all of the results where the speed has a low setting and calculate the mean roughness when the speed is low. And then I do the same when the feed has a high speed, so all the high values, and calculate the mean roughness. And then I make the same type of plot. This time we can see there's a lot more variation relative to the slope. So although it looks like there's a trend there, it might not be so strong relative to the noise. Again, this error bar represents the effect of all of the other variables, speed and temperature, varying whilst the feed is at a low value, and the effect of all the speed and temperature changing whilst the feed is at a high value. And this is quite large relative to the slope. So maybe this is not as significant. We can test whether it's significant doing a statistical test, of course, which is what we're going to come on to later. I mentioned before that the one factor at a time experiment, the experimental method, often misses interactions. In this table, I've included interaction effects. So T times S means the interaction between temperature and speed. F times F means T times F represents the temperature feed interaction, and T times S times F represents all 3 interactions. Actually, I've just realized I've missed one column. There should also be an interaction between speed and feed, which should be here as well, which you can easily do. That will make nice homework for you. So you can do the speed and feed interaction. The way you calculate these coded values is just multiplying the codes for the corresponding factors. So for example, the temperature times speed interaction is -1 times -1 gives a +1. And then -1 times -1 gives a +1. -1 times -1 is -1, and so on. And we can go through and write these codes out. Or we can look at the 3-factor interaction. So now we have -1 times -1 is +1 times -1 again is -1. That's how we get this -1 in the temperature and speed and feed interaction. What this basically means is if the two codes are the same, we will have a high level. If the codes are different, we have a low level. So this is how we can plot the interaction effects. So we use the same method as before. We calculate the average effect when the interaction is high. So this example here is a temperature, speed, feed interaction. So these are all the high values, R2, R3, R5, and R8. And these are all the low values, R1, 4, 6, and 7. R1, 4, 6, and 7. You can see we have an interaction all being negative. And then we just plot them in the same way. Usually, it's quite rare that you'll have a 3-factor interaction. There's often a 2-factor interaction. So in this case, you can see that the 3 factors don't significantly change the slope of the curve that much. And the noise is quite large compared to this slope. So this would probably not be significant. A significant contributor to the output. But the temperature times speed and the temperature times feed, or the speed times feed, are more likely to have some impact on the output of the experiment. So that's the interactions. Yeah, I've just written the interaction equation at the bottom there. So as the number of factors in the experiment increase, the number of effects that can be calculated or estimated also increase. So for example, if we have 4 factors here, now we have 4 main effects and 11 other interactions. Or if we increase the number of factors to 6, we'll still have 6 main effects, 1 for each factor, and 57 interactions that can be calculated. So there's a lot of, if you're doing this by hand, it will take forever, but there are a lot of calculations that we could do to understand which factors and which interactions are significantly impacting the performance of our design or our experiment. However, there's a principle called the sparsity of effects principle, which usually states that the most dominant effects are the lower order effects. In other words, the main effects, the effects which are directly related to the factor, and 2-factor interactions. These higher order interactions are extremely rare and usually can be ignored. And you can of course prove whether they can be ignored using statistics. The fact that many of the higher order interactions can be ignored is actually a great help. Because we can actually simplify, or not simplify, we can reduce the number of experiments that we have to do. And this is what one example is the half fraction designs approach. So let me try and give you an intuitive understanding of why this might be. If you look at the 3-factor experiment from earlier, we had 8 different experiments that we had to do. And for the low value of temperature, we had 4 different temperatures that we calculated the results for, with the speed and the feed varying. And the high value we also had 4. If we halve the number of factors here, so we just look at a couple of high values of temperature and a couple of low values of temperature, we will still have quite a lot of information about the effect of temperature with the speed and feed varying, right? So there's redundancy here. We have redundant data if we're only interested in the effect of temperature. And there's a clever way of looking at this using a hypercube method, which we will show in a few more slides' time. But essentially, by cleverly selecting which experiment we do, we can actually halve the number of experiments we do without really losing any low-level interactions, information about the low-level interactions or the main effects. we will lose some information, which is going to be the highest order effects. But the lower level effects, the lower level interactions, we can actually get it by halving the number of experiments we do. So that's a big advantage. If you have to only do half the number of experiments but still get the main information, that's a useful method, which I encourage you to use when you've got many factors. At the beginning of today's class, I showed you this example for 3D printing for a 3-factor experiment, where we have feed, speed, and temperature of the 3D printed filament. And with this, you can see that there are 8 different experiments that we can do, 8 different combinations of temperature, speed, and feed. So this can be represented as a cube. And if we do all 8 experiments, we're actually looking at the combination can be represented by each corner of this cube. However, if we only select the points which are shown with these circles, these sphere objects, with only 4 sphere objects, I can actually break this down and project onto each of the factor axes, the 2-factor axes. So for example, this BC axis, which in my diagram would represent speed and feed, I can look at the effect of varying speed and feed together and see this information. I can see the main effects of speed and the main effects of feed, and I can also see, by looking at the diagonal, what happens if we change speed and feed together. So I'll see the interaction. The same applies for, what would this be, speed and temperature. If I project these 4 points onto this axis, I have a 2-factor experiment of temperature and speed. So I see the effect of changing the speed, which is a vertical. I see the effect of changing the temperature, which is the horizontal. And if I look at the diagonal, I see the interaction between temperature and speed. And the last combination is temperature and feed. Temperature on the horizontal, I get that I can understand the effect of temperature, whether it's significantly impacting the design or not. And I can also see the impact of feed. And if I look at the diagonal, I can see the interaction between feed and temperature. So this shows that with just 4 points, 4 of the 8 possible experiments, if I cleverly select these particular corners, or conversely the opposite corners which aren't selected at the moment, I can get a lot of information. I can get all the main effects, and I can get some of the interaction information by splitting this cube into 3 2-factor experiments, essentially. So as an example, let's take the 3 factors from earlier, temperature, speed, and feed. We would have 8 different experimental combinations of these 3 factors that we would do if we were doing a full factorial design. However, by strategically picking those 4 corners, which I showed on the previous slide of the hypercube, we can see now that there are just 4 different experiments that we would need to do, and we've identified which combinations are important to get all of the temperature effects, the speed effects, the feed effects, and the interactions. So just as before, if I wanted to calculate the low value, the average effect of the low value for temperature, when the temperature is low, I would take these 2 values, R2 and R3, and the average effect with temperature being high, which is experiment 5 and experiment 8, result 5 and 8. And this time I'm not dividing by 4, I'm dividing by 2, because I only have two results. I've ignored half of them, right? Half of the results when the temperature is high and when the temperature is low. And then I can see the main effect. So this is exactly the same as before, only I don't quite have as strong statistics, because I don't have as many results included in this calculation, but I should still be able to see whether the main effect is there or not. And I can do this for all of them. I can do it for the speed, the low values, and the high values, calculate the main effects. and the feed, and also the interaction. So as an example here, I'm looking at the T times F, the temperature times feed interaction. Again, exactly the same as before. T times F is low at experiment 2 and experiment 5. So we have 2 and 5 for the low value, and it's high for experiment 3 and 8. So T and F 8 is high and 3 is high. So I take these values and calculate the average, and then I can see if there's an interaction between temperature and feed. So I hope you realize the power of this. We've significantly reduced the amount of work that we have to do, but we're still able to get pretty much the same information. And the reason we can do this is the sparsity principle, and the fact that the higher order effects are usually negligible. So far I've showed you how to do a full factorial experiment and a half factorial experimental design, and I've shown you how to create the main effects plots. But once we have the main effect, we need to understand whether it is really significant and larger than the background variation. So to do that, we need some sort of statistical approach. So this brings us right back to ANOVA, which we were studying last week. Last week we were studying single factor ANOVA, where, for example, maybe just the temperature is changing and we change the temperature through several different levels and calculate whether that factor had an effect. Now we have to do multi-factor ANOVA, and I'm going to show you a two-factor ANOVA, two-way ANOVA today. And then in the class next week, we will use higher order ANOVA analysis, but we will use a computer to do that type of analysis. We won't use it using the equations which I'm about to show you today. So this is just a very quick ANOVA refresher. Remember, ANOVA looks for large between group variations and small in-group variations. That means if there's a large between group variation, it means that the treatment is having an effect on the output of the experiment. So for example, if the factor that we're playing with is temperature, and we increase the temperature and we get a much smoother print, then the between group variation for the different temperatures that we're measuring will be large. And the in-group separation, in other words, the noise, or how much within each temperature setting the measurements are changing, should be very small to to get a significant effect, to understand that the temperature effect is significant. Or oppositely, if these in-group variation is large and the between-group variation is small, which is this case here, then we would not be able to say with any statistical confidence that the treatment is having an effect on the output of the experiment. So if we go back to the two-factor experiment from earlier, where we're trying to optimize the roughness of a 3D print, we had the factors speed and temperature. This time I've added an extra level here, so there are 3 levels in this experiment. For speed and 2 levels for temperature. Now, for each of these levels, we can, each of these factor A, factor B, speed, temperature combinations, we can conduct 2 experiments, 2 replicates. We repeat the measurement twice. So we have some idea of the repeatability of each measurement combination. And I've labeled here the number of levels in treatment A, or factor A, is for speed is 3, because we have 3 different speeds, and the number of levels in factor B is 2, because we have 2 different temperatures. So these numbers are important because it will help define the degrees of freedom. The other thing I've done is calculated the average effect for each of these different factors. So when factor A is changed at each level, I've calculated the mean of the mean of each each feed. So when the speed is low, I have a value of 0.33, which is the mean of these four numbers. This 0.325 is the mean effect at 150 millimeters a second, and then same for 180 millimeters a second is the 0.37. So you can see here by looking at these numbers that you might think that as I increase the speed, the roughness is getting higher, or this number is getting larger. And the same applies for factor B, which is temperature. So here I've taken the average of these 6 measurements, which is the roughness at each at the 3 different speeds, and I've done that again for the higher temperature. So I can now see roughly, but I don't know if it's statistically significant yet, but I can see that as I increase the temperature, the roughness gets lower, and as I increase the speed, the roughness gets higher. But as I said, we don't know if this is statistically significant, and we haven't really analysed the interaction effects, so the diagonal along here. And that's why we're going to use now two-factor ANOVA. So these two-way or two-factor ANOVA equations should look quite familiar. They're very similar to the one-way equations that we used earlier in the week. So for example, to calculate the treatments, the sum of square treatments for factor A and factor B, we look at the average at each level of factor A, and for the A factor was speed, I think, in the previous table. So there are 3 different levels, and the right-hand column was the average at each level. So that's what this represents, and we deduct the grand mean, square it, and we will get the sum of squares when we add all these different levels together. We have to multiply by b times r because there are 2 replicates and there are 2 levels for factor b. So we need to multiply by 4 this total to represent the total sum of squares for all of these different averages. And the same applies for SSB. Again, we look at the bottom row of the table on the previous page, which shows the temperature effect, and we look at the difference between the grand mean and the mean at each level of factor B, at each temperature, square it and multiply by 3 times 2 replicates and 3 levels of factor A to get the total sum of squares of factor B, of treatment B. The sum of square errors is the mean at each speed temperature combination. So for each speed and each temperature, we took some replicates, so we can calculate the mean of those replicates, and then we subtract it from each of the 2 replicates and square it, and that will give us the sum of square, the square difference for each speed and each speed temperature combination. So for each speed temperature combination, we find the difference between the mean and the individual measurements, square them, add them together, and that will give us the sum of square errors. The total sum of squares, calculated exactly the same as one-factor ANOVA. We look at every measurement, deduct the grand mean, square them, and then we'll get the total sum of squares when we add everything together. The total sum of squares is the total kind of variation of the whole data set. There's one critical part that's missing though. I said earlier that we can calculate the interaction effect as well. The total sum of squares is equal to, it has to include the interaction effect. We don't really have any way to calculate that from the individual measurements, but what we can do, because we've calculated the total sum of squares and we calculated A, B and the square errors, we can just deduct these from the total sum of squares to get the sum of square treatments. And then we have all the data we need to do a two-factor ANOVA statistical test. So this slide shows how to calculate the mean squares for the treatments. So we take the sum of square errors, the sum of square treatments, or the sum of square errors, and divide by the number of degrees of freedom. A is varying for A different levels. A was the speed effect, right? So there are 3 different levels that we chose. So there are 2 degrees of freedom. B was a temperature effect. There are 2 temperatures. So 1 degree of freedom. So that B 2 minus 1 is 1 degree of freedom. The mean square error is the sum of square errors. If you remember, this is like the variation within each combination of speed and temperature. So we have to consider that the mean of each of those means for each combination of speed and temperature was made up of 2 replicates. So if we calculate the variance, we have to do the Bessel correction on that. And then, of course, there were A times B different boxes. In other words, 3 different levels of A and 2 different levels of B. So we had 6 different combinations with the Bessel correction done here. And this is the equation for the mean square term for the interaction. We take the sum of squares for AB and divide by this, which will give us the mean square of the AB interaction. Again, all of the degrees of freedom should add up together. So this is the treatment A, degrees of freedom, treatment B, degrees of freedom, the error term, degrees of freedom, and the AB interaction, degrees of freedom. So that simplifies to this if you do this maths. So now we have the sum of square, the mean sum of squares for all of the factors and the interaction terms and errors. So we can calculate the F statistic. So just as one way ANOVA, the F value, the F statistic, is the mean square of the treatments divided by the mean square error. And this time, though, we have 2 different treatments, A and B, and we have their interaction, 2 different factors and their interaction. So we can calculate the F statistic, and we can also look up in the tables or using Python. We can look up the critical value corresponding to the degrees of freedom for each of these ratios. And if this F value is greater than the critical value, then the treatment or interaction would be significant. By combining this knowledge with the main effects plots, we can actually build an empirical model to predict how the system behaves. For example, how the roughness of the 3D print depends on the different factors and interactions. In that model, it would only be necessary to include the factors which are significant. In other words, the factors which have an F value greater than the critical value. Because the other ones, we already know the statistical test tells us that it's just not worth considering. It's not significant. It's insignificant. I want to show you a real example from SUTD research. In fact, it was one of my students that did this. He's a material scientist, and he wanted to design a process for growing a hexagonal crystal like this. In these hexagonal crystals, we have very beautiful layers of atoms, and this is very important for certain types of data storage. If you look down on this crystal structure, this is the side view and this is the plan view, you can see that the atoms are arranged in a hexagonal form. So to get the atoms to arrange in this form with a top-down view, we need to very carefully control the temperature of, sorry, not just the temperature, we need to control many factors that affect the growth: temperature, pressure, power that we deposit these materials down with. And then if we get the combination exactly right, we will get beautiful hexagonal crystals forming. Very characteristic X-ray diffraction pattern. So what my student did, Jitendra as a student, what he did was look at all the possible combinations of temperature, power, pressure, a buffer which we put underneath the material, and the type of buffer. And he did exactly as I showed you today. He did a half factorial design, a half factorial experiment. So he has 5 factors here, 1, 2, 3, 4, 5. And for each factor, he assumed a low value and a high value. And then that meant that he had 2 to the power of 5, which is 32 different experiments to do. But that's a lot of experiments, and these experiments take quite a lot of time. So he did half the experiments through a half factorial method. And then he calculated the result. And he actually used X-ray diffraction to measure the quality of the crystals and how hexagonal they were, essentially. And this is what this number represents. So these are the individual experiments and the X-ray diffraction patterns that you can see here. And you can see some experiments have very intense peaks in certain positions. Other experiments have very weak peaks or hardly any peaks at all. So you can see that definitely something is changing. The quality of the samples are changing in some way. He used ANOVA, then multifactor ANOVA, because he's got more than 2 factors now. He has 5 factors. So he used multifactor ANOVA to have a look at all of these different parameters to see which parameter significantly affects the quality of the quality of the hexagonal crystals that he was trying to grow. And you see that the buffer type, the material he was growing on, was the most significant, and then temperature and power and so on. And then all of these interactions and the buffer thickness had an insignificant effect on the quality of the crystal. He also plotted the main effects plots, and with these main effects plots, he was able to create a statistical equation, an empirical equation to predict how high quality crystals could be grew. And after following this process, this factorial design process, Jitendra achieved beautiful hexagonal crystals. So this approach really does work, and I can tell you that it was significantly faster to do this approach than 1 factor at a time, which others in my group had tried before. Jitendra was able to get beautiful results in a much shorter time. So I really encourage you to try this multi-factor factorial design in your work in the future. Although in this presentation I've only shown you how to do 2-factor ANOVA or 2-way ANOVA, as you can see from Jitendra's work, it really is possible to do multi-factor ANOVA with as many factors as you like, but you need to use a computer. So that's something that I'll be showing you in the coming week. In summary, multi-factor ANOVA can be used to evaluate and compare different configurations of an experiment or even different configurations of a design. And you can do that. You can do this statistically, and you can use the results to build a model. Although I haven't showed you how to build the model today, and a statistical or empirical model to predict the performance of your design. So in the coming week, you'll be using ANOVA, multi-factor ANOVA, in design of experiments to design a propeller that can generate as much thrust as possible with as little input energy as possible. That's going to be the main aim for the coming week. And you'll need to use multi-factor ANOVA to do that. Okay, so good luck, have a good weekend, enjoy, bye.